Hello, my name is Bisqwit. I hope you are having a great day. It's been a long time, never mind, let's get straight to the point. When I was a beginner programmer, one very interesting question that I eventually ran into was this. When I'm making a game, there's lots of things that must happen simultaneously. The game must be reading users' input, the actors must animate there, the enemies must move, the game must be checking collisions and so on. And it all must happen simultaneously, and I just couldn't figure out how to do it. How do I make several execution heads that are running simultaneously through the game program, each their independent path? A friend of mine who was a significant mentor to me at the time then told me that I don't really want to have things running simultaneously. Well, it was what I wanted, but it wasn't what I was supposed to want. He told me that the main program or the main loop of the program is supposed to run things in sequence. First you check the player's input, then you possibly animate the characters, then you run the enemy AI and so on, each task in sequence, one after one another, and then you go back to the loop and it starts again. And it is all done several times in a second, many times in a second, and this was a significant aha moment to me. And this realization carried me very many years, even when I migrated to Linux and I was creating server programs that were handling hundreds of concurrent connections at the time. But there are some tasks that benefit from concurrency, especially now that multi-core processors are becoming more abundant in desktop computers. Certain types of programmers can no longer ignore the concept of threads. My video is not going to be a beginner's tutorial on thread programming, since it's a way too large topic to cover in one video. In fact, I expect the viewer to be already somewhat learned in the topic in general. Instead, I will explain the tools that modern C++ language provides for the task, given that you already know what you want. Let's begin with a simple example program. Let's create a program that downloads files from the internet. These files are from the Unicode consortium and are intended to be machine processed. Because I don't want to cause undue load to their servers, I am mirroring these on my own server. Now, standard C++ doesn't currently provide any facilities for network connections, so I am using a third-party library called CURL for actually downloading the stuff. It is pretty easy to use. The file will be saved on the disk. To keep the program simple and to the point, I'm not doing any error handling. I will let the library do that. For the user's convenience, the program will also show the download progress in real time. The \r is a special character that returns the cursor to the beginning of the line. Its purpose is to refresh the same line instead of printing new lines. Please make sure you are compiling a C++14. You must also link the CURL library in, and it is a good practice to compile with all warnings enabled. There, that was just to make sure it works, and for sure we can do better. Next, let's extend the program to download multiple files. Since we are working in the context of Unicode, my choice of sample files is the different ISO 8859 legacy codebase mappings. Let's download all of those. There are 15 of those files. At this point I am also adding some more sophisticated cursor and color handling functions that will be useful later in this video. The progress of each download will be shown on a separate line with some simple color formatting. I tried to make this decoration that is not the point of this video as non-invasive as possible. Let's compile the program again and run it. To make things interesting without consuming tons of resources, my server is simulating a slow dial-up and only pushes these files at a rate of 4 kilobytes per second, and the download seems to be taking ages. Nowadays, who has the patience to wait until all the 15 files have downloaded at this speed? Although patience is a virtue, as a programmer maybe there's something we can do to make this more comfortable for the user. This is where threads come in. The thread object is initialized with the functor and the list of parameters to pass to that functor. While this syntax works, I am more comfortable with using the lambda function here. Before the thread object can be destructed, the thread must either be detached which means it will run completely independently on the background like a ghost, or joined, which means the owner of the thread explicitly waits until the thread is completed. Failing to do either will result in the program aborting. Now when we compile and run the program again, the download should complete way faster than the previous time. In the single-threaded program it would have taken 36 seconds, but I interrupted it after 14 seconds. Now it took about 5 seconds total, but the screen was a total mess. What's going on? The reason is that all these threads were outputting to the screen simultaneously, even in the middle of the cout expressions run by other threads. I will explain this topic later in more detail, but for now suffice to say that addition of these two lines will provide perfect mutual exclusion. To prove it, let's run the program again. Let's move on. We successfully made each thread independent. What if we want to print the total number of bytes downloaded? We would have to combine the download lengths from all threads into a single focal point, an integer variable. Here is the simplest way to do it. What could possibly go wrong? We will see about that. At least it's not crashing. How about when we run it again? The totals do not match. These numbers are way smaller than the expected total, and they are different each time. I'm pretty certain I didn't put a random number generator in this program. Okay, you already know it. We already saw this earlier. The value gets modified by another thread in between of the read and the write hidden in the addition expression. The simplest way to fix it is to make the variable atomic. I will also cover this topic later in detail, but for now as an introduction you can see that this fixed the problem perfectly. Now the numbers match. For an exercise, let's save the sizes for each individual download and sum them together. If you paid any attention earlier, you can already guess what is wrong with this code. No, just kidding. The program just crashes randomly. This is not a bug in the compiler, nor in the standard library. As before, the solution is to add mutual exclusion to the vector modifications. Request exclusive access before modification and release it afterwards. But this is not the best we can do. The lines we most recently added can be significantly simplified by using asynchronous functions and future objects. We don't even need to join the threads anymore. This future object is a strange new friend, and I think it would be wise to study it in more detail to see what it can be used for. The future is a variable that can be written once and read once. You could think of it as a mailbox. This special mailbox is only valid when someone is sending you mail. If no one is sending mail, then the box is invalid and without purpose. You can wait until the mail arrives. You can wait for any user-defined duration, including 0 seconds. You can also wait indefinitely, but then the program will hang if the sender never delivers. Calling GET will wait until the mail arrives, and then gives you the mail. You can only fetch the mail once. Furthermore, you cannot place mail in the box yourself. The mail has to be sent by someone. One of these senders is called a promise. It's a promise to send mail. The mail is sent through the promise object using its setValue method. The mail can only be received once. Once it is taken from the mailbox using the get method, it is no longer there and cannot be fetched again. Likewise, the promise can only be fulfilled once. Calling setValue again would produce an exception. You have already delivered the mail you promised. There is also a shared future object that allows fetching the same mail multiple times, even in different threads. You could think of it as a bulletin board. Now, there's very little practical purpose in using these highly abstract devices in a single-threaded program. and there are many different ways to use these future objects, one after another more and more abstract. I created a simple testbed program to illustrate how each of these little devices work. The future object will be subject to the same treatment in each test. I will just continue calling it mailbox in my tutorial, because it is much easier to pronounce than future object. The mailbox can be in 4 distinct states: timeout, ready, deferred, and invalid. Timeout means that the mail has not yet been delivered. Ready means it has. Deferred means it will only be delivered when you call get. And invalid means there's no sender. In our test we first print the current state of the mailbox. We do the same in the end. In the between we will wait 2 seconds for the mail to be delivered, printing status every half a second. After the 2 seconds, or if the status is ready, we call get and print the mail we received. It is also possible the sender sends an exception instead of mail, so we have to be prepared to receive an exception. Because we are dealing with threads, I am adding a sleep function to make it easier to demonstrate the asynchronous nature of the mailbox. You cannot create mailboxes yourself. Well, you can, but the only thing you are ever going to receive through it is exceptions. The certified senders are the async function, which has 2 options, asynchronous and deferred. The promise, which is a one-way channel for passing a single message. And a packaged task, which is like std function, but when the function is called, the return value is put into the mailbox. And technically speaking, share in the future itself. All of these facilities can send exceptions instead of actual values. Now it is time to compile and run our testbed, so that we can get to study how each of these little devices work. First we have the mailbox without any sender. The future object is constructed with blank arguments and immediately sent to the testing. On the right you can see the source code. On the left you can see that the state of the mailbox is immediately invalid. Because it's invalid, there's no sense on waiting on it. Calling get will produce a std future error. Then we have the asynchronous function. Calling wait will give you a timeout status, as long as the asynchronous function does not complete before the timer expires. Here the function did not complete in 2 seconds. When get is called, the return value of that function is produced, which is 7 here. The blue async start and async end markers are produced by the asynchronous function itself, as it is clearly running on the background independently. The deferred function is the same, except that there's no timeout status, and the function execution only begins the instant you call get. Most likely this does not use threads at all. We covered the promise before. When you are using promise, the mail is sent using the setValue method rather than as a return value of some function. Here we also see an example of how the delay expires in the middle of one of these wait calls. The wait method now shows the ready status. In the next example, the promise is used to pass to another thread any arbitrary exception that is thrown in some thread. Here the thread begins execution in the middle of a wait call. After the second wait, the mailbox is signaling ready status, meaning that something was received. When you call get, you get to see that it was an exception that you received. The exception is received exactly in the shape it was sent. Finally, the packaged task. The packaged task wraps a function much like a std function does. However, it combines the behavior of std promise and std function. The return value of the function is sent to the mailbox rather than to the caller. The mailbox receives the mail when the packaged task returns. Up until the task has not been called or returned, the box still shows the timeout status. Now let's study mutual exclusion for a bit. Mutual exclusion, or mutex for short, is one of the fundamental tenets of concurrent programming. Let's begin gently with a small example program again. Since it has been 2 days since the program code where I handled logs and atomic variables, for me anyway, because it takes days for me to record this stuff, let's refresh our memory a bit. Here is a simple example program that runs 2 threads. both of which increment the variable 1000 times. What is the value you would expect the program to print? Let's try it out. Note that this is a rather benign result. On some platforms you could receive a bus error instead, crashing the program. Now, if you paid attention earlier, you would know that the simplest way to fix this problem is to make the variable atomic. When the variable is atomic, it means that the operations such as increment, which comprise of a read, modify and a write, are packed into an inseparable group, and other threads cannot access the variable while these operations are taking place. In other words, the basic operations on the variable are atomic insplittable. However, atomic operations are only available for certain basic types. If we change the counter into a floating point number, the increment expression will not compile. There is still a way to rewrite the expression, but it is rather complicated. Now suppose we have an even more complicated type, such as std vector. How would you make this safe? Wrapping the vector in std atomic will not work. It wouldn't make any sense, and it's not designed for that purpose. Would it be possible that we don't even need to do anything? Let's compile and run the program and see what happens. Oh yeah, sometimes it works, but other times you get assorted errors. This is because the standard containers are not designed thread safe. They could be, but a very fundamental principle in C++ is that you only pay for what you use. Since making containers thread-safe would require some extra code that would needlessly weigh down a single-threaded program, the STL is not thread-safe by design. If you do need mutual exclusion, you have to write it yourself. Luckily, it is very simple to do so. Just lock a mutex before access and unlock it afterwards. The library contains a few specialized types of mutex objects, but I'm just going to cover the simplest one here. This is how you would do it in C2. Now those of you who watched my second tutorial on C++ for C programmers remember why we program in C++ and not C. That's right, resource acquisition and release. Locking a mutex is a form of resource acquisition, and unlocking is releasing the resource. The resource is the exclusive access. Now what happens if we insert an alternative execution path to the loop, such as a break statement? Now there's an execution path where the mutex is never unlocked. This may happen accidentally, and it is very common. It causes the program to hang because the thread is waiting for a mutex to be released, and it never will. The way we solve it in C++ is classes. When we instantiate lockGuard class in the scope, the lock will be automatically locked at the opening brace and unlocked at the closing brace, no matter which route is taken out from the loop. It is foolproof. The lockGuard really does nothing else than call lock in the constructor and unlock in the destructor. If you need conditional locking or alternating between locked and unlocked while still reaping the full benefits of compiler-enforced resource ownerships, you can swap the lockGuard for a unique lock. Again, you only pay for what you used, and that's why the library is offering both options. The next, 4th, 5th, 7th topic anyway is the condition variable. A condition variable is what you use when one thread is waiting for another thread to do something in particular. This is the downloader program from earlier. Suppose we want to do some post-processing on the files. We elect to use multi-threaded pipeline architecture. There is one thread that produces files by downloading them from the internet and puts them into a stack, and another thread that consumes files from the stack and does work on them. This is called a producer-consumer architecture. The benefit of this design is that the producer doesn't need to pause for the duration of the processing, but can keep downloading new files without interruption while the other thread is doing work. In this example program, the work that the consumer does is to print lines containing a certain text pattern. By now, if you paid any attention during this video, you should already be able to see something terribly wrong in this program. Let's run it and see. Oh yeah, precisely as planned. Not. So what was the thing we needed to do to fix this? Do you remember? Mutex. DOSBox. Right, so anytime we are modifying the container while there's a chance someone is reading it, or modifying the container while there's a chance someone is modifying it, or reading the container while there's a chance someone is modifying it, we must have exclusive access to it. Any of these operations must be surrounded with locking the same mutex. There are really only two situations where you don't need a lock. That is, when all concurrent accesses are const type, and when there is absolutely one thread at most accessing the container. Multiple concurrent reads do not need mutual exclusion if no one is modifying the container at the same time. There are also lock-free containers, but currently the STL does not have any. Now the program works and no longer crashes. However, upon closer examination we find that the program is consuming tons of CPU time while it is running. Indeed, the CPU utilization measures at 100%, even though most of the program's running time should be spent waiting for files to download. There is still something wrong with the code, even though it accomplishes what it's designed to do. In the consumer function, the outer loop is waiting for end to be signaled. If the end has not been signaled, the files are checked. If the files are empty, the loop continues. If the end flag has not been signaled but the file stack is empty, the function keeps spinning at maximum speed. This is called a busy loop, and it is considered very bad style. The program is consuming maximal CPU time while producing absolutely nothing. That's where std condition variable steps in. The condition variable is used by the producer to notify the other thread when one of these things have changed, and the consumer will wait on the condition variable. While it is waiting, the thread is totally sleeping and not consuming any CPU time at all. This saves electricity, keeps the CPU fan quiet, and prevents the system from slowing down. It is an all-around beneficial thing in every regard. Now when we run the program and compare the previous version A with the new version B, we see a very tangible improvement in the CPU utilization. And this concludes my lesson at this time. Thanks for watching, see you next time, bye! Do you see the change? A couple of instructions changed a bit, but it's still basically exactly the same code as the C version was. Conclusion: rewriting your code for greater clarity, greater reusability and greater extensibility by translating it into C++ will not hurt the performance.